Okay, today too our lecture might be a little short depending on scenario, but we'll pick up pace from the next one onwards. Okay, so today we'll start our discussions about model-based navigation systems. So far we have looked at guidance systems where we looked at the idea of line of sight based guidance mechanisms. We even looked at trajectory tracking, target tracking, path following, how to formulate a path given a set of waypoints, and then how that reference trajectory can be fed into a control system for which it is trying to compute the error between the desired trajectory and what the actual trajectory is, and then feed that error to the controller in order to drive that error down to zero. That is what we have seen so far. But in all of this effect, we have assumed that there is like a perfect knowledge of what is happening to the craft, as if we know everything about the craft precisely. We know how far, what is the position of the craft, what are the velocities of the craft, what is the orientation of the craft, what is the accelerations of the craft. We assume that this is precisely known, but reality is something different. The reality is that this is not precisely known, and we have to measure it using different types of sensors. So this topic will mostly be talking about navigation, where we'll be understanding as the sensor data comes in, how do we estimate the best estimate of the full state vector of the vehicle and use that in order to control the vehicle. So we have the controller part and the guidance part fixed in place, but we need a best estimate of the state of the vehicle at every time step so that we can feed it to our controller in the feedback loop. And you'll see that it's not just a problem of that. We may also need to manipulate that estimated signal in order to only estimate some low frequency components and avoid some high frequency noises so that we are not putting too much wear and tear on our actuators. So in that sense, we need to spend some time to discuss about the so-called model-based navigation systems. Now, figuring out sensors and Kalman filters for sensors and having a complete state vector estimation for the filters itself is a topic of its own. So we are not going to embark on that purely or completely in this few lectures that we have left. But our target will be to understand that as measurements are coming in, how to formulate the best state of the vehicle. And in case if there are lapses in measurements, so let's say that some sensor malfunctions and we are not getting the output from the sensor, how to account for that and still be able to so-called figure out what is the current state of the vehicle based on a mathematical model. And that kind of amounts to the idea of what is called as dead reckoning, which means that in the absence of a sensor, we are still trying to, based on the last measurements which we have, we are trying to understand where we might be at the current location. Of course, when the sensors start giving us more information, we will be able to again figure out where our localization issue is. But until that time, we should be able to continue to do this. So that is kind of the agenda when we talk about model-based navigation. It's called model-based because we have a model of the craft which we are emulating and which we are updating with measurements which are coming in from our sensors. Okay, so before we go further and discuss about all the different model-based navigation systems, it's wise to spend a little bit of time to talk about what are the different sensors which we have on board a vessel and how do they work. So we'll spend today's lecture mostly on that, and from the next lecture onward, we'll try to start looking at more mathematical details. So some of the typical sensors on board a marine craft is an IMU, which is called as an inertial measurement unit. And usually this is composed of 3 accelerometers, 3 gyroscopes, and a magnetic compass. On magnetic compass, and sometimes it also includes some other measurements as well. It may include more measurements as well, but that's what typically an IMU will consist of. And then you have the GNSS, or the Global Satellite Navigation System. And this basically gives you a latitude and a longitude. That's what you typically get out of GNSS systems. And then you may have a typical magnetic compass or a gyrocompass, and we'll try to understand what is the difference between these two, how are the two different, and which one is most widely used on ships. You'll see that it is usually the gyrocompass, which is used on typical ships, but if you have a really small craft, you may want to avoid spending money on gyroscope or gyrocompass, then you may be looking at magnetic compass as the way to go. Okay, typically GNSS positions, like the global navigation satellite systems, can be classified usually into 4 different constellations that there are there. The first one to come up was the Navstar Global Positioning System, or the GPS, and that has kind of colloquially become the name today for GPS systems. So this was started off by the US. So USA started this, still continues to be owned by USA, was primarily started off for military purposes in the 1980s. When they started off, they did not have global coverage, which means that they could not localize anywhere on the Earth. They could mostly localize primarily in the US airspace. Later on, they extended it, so they had multiple constellation of satellites put in place. Typically, I think they have a 24 set of satellites which are typically operating at each time. And they are usually replaced, serviced, and old satellites are degraded. So new satellites are launched to keep that number of 24 in place, okay? So that you can get a global positioning system, worldwide coverage can be ensured. Now there are private players who want to play this game as well. And I think you might probably have heard of Elon Musk's Starlink, right? He wants to put more satellites in orbit and be able to give a much, not only propose a high-speed internet, but also it will help with commercial GPS applications. So Navstar still continues to be primarily military-based application, although now it has kind of diversified quite a bit into the commercial space as well. At one time, Navstar GPS would add an erroneous signal to their carrier signals so as to actually make it difficult for commercial applications to get a very precise estimate of their GPS. So it was done on purpose. So they wanted to make sure that others do not have the ability to localize using Navstar GPS, but only their military grade should have specific access to those channels. But I think that has stopped now. So nowadays that happened during the Cold War with the USSR, and that's why USSR developed their own navigation system, which is called as GLONASS. GLONASS also did not have worldwide coverage for a long time. They developed worldwide coverage almost close to 2000s. So they have been around since 1990s in competition with Navstar GPS, but they did not get worldwide coverage, or they did not bother to go for worldwide coverage. It was only in the early 2000s that they went for global coverage. Again, in the 90s, once they went for global coverage, they did not keep it up. So at some point later down the line, they lost worldwide coverage. But then again, I think since 2011, they have been maintaining a worldwide coverage, and now it's more or less active. Then came the Galileo constellation, which is from European Union. So once it was established that we actually need this for localization purposes, and we are looking at more autonomous driving and autonomous vehicles, they're coming into the picture. Europe decided that they will start off their own commercially available constellation, and Galileo has been a very recent addition. I think they have started to give worldwide coverage very, very recently, sometime in the last 5 years. The other last constellation is called Baidu, and that has come from the Chinese constellation. They too did not have worldwide coverage for a long time. I think since 2020 they are offering worldwide coverage. Otherwise, they had pretty good coverage over the most of the geographic regions, but worldwide coverage has been started off since 2020. India also has its own GNSS positioning systems, which does not have worldwide coverage yet. Okay? We have coverage over the regions of India, Pakistan, and neighboring states, so that if we wanted to position somewhere, we can at a time only geographically position our satellites to look at a certain geographical region and position within that region. So we don't have worldwide coverage yet. Okay, so from the first point of view of a surface vessels, our most interest is usually in the search, sway, and the yaw motions. And typically when we are looking at the sensor suite, you're looking at positions measured using a differential GPS or differential GNSS. And the heading is usually measured by either a magnetic compass or a gyrocompass. Now, you might have additional sensors in place, like an IMU, which can measure accelerations, gyroscopes, in order to give you angular velocities, which can then be used to estimate orientations as well. But typical old generation ships, like back in the day, you would see that they would be either having a GNSS for positions and a compass for the heading. So that would be the minimalistic living of what you would call. But today that's no longer the case. Most of the time you'll be equipped with multiple GNSS and other sensors as well, like LiDAR, radar, and things like that, which can aid you in navigation much better. They also aid you with perception, which was not of concern back in the day, but it is of more concern today. All right. So as I said, these additional sensors could be IMUs, hydroacoustic positioning sensors, laser sensors, which LiDAR is a part of. Does everybody know the full form of LiDAR? What is the full form of LiDAR? No? You've been using it left, right, and center for your VRX competitions. Never bothered?
Sir, light detection and ranging.
Light detection and ranging. That's right. So it's how does LiDAR work?
So it sends a laser beam
from
it, and then it reflects from an object at a distance, and then it is received. The LiDAR receives the beam back. Then based on the time of flight, it calculates the distance to the object.
Time of flight?
Like the time it takes to send the beam there and receive it.
Are you sure?
Yeah.
With a radar, that is the case, probably, because the distances are large. You're looking at about 200 kilometers, maybe 200 meters or 250 meters to a couple of kilometers. But with respect to close,
I think it works on the similar principle of radar.
Not quite, actually. You see, because the light will travel at 3 lakh kilometers per second. So just imagine if 5 meters is the distance you want to measure. What is the time difference?
The time will be very small.
Yeah. How can you ensure that you measure that much of a time delay? Never wondered about this, did you? How does it measure then? If it is not with the time delay, how does it measure? Now Shatab should not answer. He just found out the answer today morning. It measures based on the intensity. How much is the intensity of the light deteriorating? Because as the light propagates through the medium, there will be some scattering. So based on how much got scattered away, it makes an estimate on the distance. So LiDAR is not just using time of flight. Time of flight will be very difficult for very short distances. It's using the intensity measurements in order to characterize how far the light has actually traveled. Okay, but then it also suffers with some aspects that some surfaces may not reflect as much, some surfaces may be reflecting more, in which case you may not get a precise measurement, and that error matrix, covariance matrix can grow in size at that time. So this is something to keep in mind when you're looking at LiDARs. We had a very interesting presentation today morning with our maneuvering and control students, where they were looking at how to fuse LiDAR and a camera measurements together. So I thought you guys have done the same for your VRX, so it must have been very interesting to see that. All right, now when we come to the GNSS, as I said, typically we are using the differential GPS for measurements, okay? Which means that we are looking at a differential GPS means that there is a fixed receiver whose position is precisely known to us ahead of time. And then once we are trying to do the triangulation based on the signals coming from the satellites, you will see that there will be some error between what you measured versus what was the known position of that base station. Now that error between what you measured and the known position is what you transmit back to your receiver. Okay, and that receiver is basically receiving this difference in errors, and it is correcting for its position estimates which it made. So you may think of it as something like this. Let's say this is the base station's known position, but at a particular instance, based on measurements, you're getting the position to be this. And the rover is at some location, and it's measuring its position to be this. Okay, I probably should mark it here. Yeah. Then based on this error being transmitted to the receiver will correct its position and mark your exact position of the rover to be here. So what it is doing is it is taking this difference in the measurements and passing it back, so that assuming that the rover and the base are not too far away and they are kind of seeing a similar disturbance in signals, okay, and then based on that it's making this assumption that the same distance, as much as the base station is away from its measurement, the rover will be also at an equal distance away from its actual position from where it is measured. So that is what is called as a differential GPS. So you transmit the position error to the GNSS receiver, and with this methodology you can get up to less than 1 meter accuracy, which means that if the vehicle is somewhere between plus or minus 1 meter radius, if it's outside that radius, you can precisely position it. Inside that 1 meter radius, you can't precisely get its position. So there is a covariance matrix which will tell you that the covariance is quite close to plus or minus 1 meter, which you have to account for in your measurement uncertainty. Now, there is a different way to correct for the error as well, and that is called carrier differential GNSS, which means that here you're not just taking into account what is the difference between the measured value and the known value, but you're also trying to take into account what is the phase of that carrier signal which is coming in. So remember that GNSS is basically nothing but it's sending an electromagnetic pulse from your or electromagnetic wave from your satellite to your GNSS receiver, and basically on what is the time dilation between when the satellite signal was stamped and sent and when it was received. You're basing that and trying to find out the triangulation of it. Basically, you need at least a minimum of 3 satellites in order to triangulate your position precisely, but you typically need a lot more in order to drive the uncertainty region down in order to get a good estimate of your vehicle. So typically you will see that if you open your physics sensor toolbox, an app which you can open on your phone and see how many satellites it's connecting to, you'll see that for a roughly 3 meter accuracy range, you need to connect to at least 30 satellites. only then you're getting a good enough triangulation. Otherwise, you're not seeing that good a triangulation come out. So this GNSS based on carrier differential is based on the idea that we are able to track this carrier wave which is coming. We are able to track the phase difference in that carrier wave as the vehicle is moving. Okay, so because the phase difference, you can also determine how far away I am. So if typically if my observer was stationary, I should see that the phase should continue to be the same no matter what. Right? Once there is a phase which I have identified, let's say that the carrier signal behaves as A sine omega t. Then that omega is fixed and my phase difference is 0. And it should remain the same for all future times. Phase is not something which will change with time. But here what will happen, because of the disturbances, you will see that the phase itself might change with time. And when that change in phase is detected, you're using that additional information to figure out how much have I moved. And that measurement is much more precise because you're now looking at within certain wavelengths of that carrier frequency, you're trying to estimate how much phase difference has come through. Typically what you will see is this overall phase measurement can be precisely or can be denoted by what is the precision of this phase measurement, which is roughly about 0.01 cycles. So how much off I am, 1/100th of a cycle, I can measure precisely using the newer GNSS receivers. And based on those measurements, I can figure out what is my error in the localization. So assuming that the wavelength is about 19 centimeters, you can assume that the error in my measurement can be boiled down to 1.9 mm. So now you're able to go from a meter level accuracy to further zoning down using this carrier-based phase-based correction, where you can get up to millimeter level accuracy. So whenever you're looking at what are called real-time kinematic or RTK systems, that is what is happening behind the scenes. You're looking at not only as to how much is the difference between a known base station and its measurement, but you're also looking at what is the phase difference in my receivers. And you're using that phase information in order to correct for your measurement to come within a much tighter error bound. Now, one of the main challenges with this carrier-based phase detection is that you do not know how many cycles of phase there is. So you can be off by 5 degrees, or you could be off by 365 degrees, or you could be off by 725 degrees. They'll all read the same phase difference, right? So the number of cycles by which you're off is something which you need to know, and that's a sensor specific thing which you need to know. If you know that precisely, then you can try to estimate it based on carrier phase difference based methods. But please understand that carrier based augmentation is not as robust as differential GPS based augmentation, which means that your accuracy within that 1 meter is very precise, whereas your phase-based method can be subject to a lot more problems or a lot more susceptible to more disturbances. I'll give you a couple of examples. When you're looking at very height, long, tall skyscrapers, there may be multiple paths for that GNSS signal to bounce off between multiple buildings before it reaches your car. And once that happens, once you have multiple paths which the signal can take to reach you, you're not quite sure where you are exactly, right? Because the time dilation will be different for each of those multiple different paths, which means you will localize yourself to be somewhere else. You're presuming that you're looking at a straight line between the satellite and you, but that need not be the only path through which you're getting the signal. So therefore, these carrier-based phase difference-based methodologies, they're not as robust as what you see from typical differential GPS systems. Okay, so whenever you see, so for example, the sensor we acquired, it promises us millimeter level accuracy. But a lot of things have to go right for us to actually see a millimeter level accuracy on the ground. Right? So you have to have a line of sight between the base station and the rover. You have to have a clear sky. There are no refractions of your signal as it is coming through the ionosphere. So all of these things have to bring into picture in order to make sure that you get your millimeter level accuracy. So it's not always very straightforward. So in the sense that it's not as robust. So this is not as robust. Okay, so that is with respect to measuring the GNSS position. Let's also now talk about heading. So sometimes you will see that you can also try to estimate the heading of the vehicle using GNSS antennas. That is somewhat we are trying to do now, right? We will be attempting it on our craft as well. If we can have GNSS sensors which are separated by a distance, and if you can precisely know a millimeter level accuracy for both your sensors, then you can even precisely know how much the vehicle has yawed. So suppose it's a 3 meter long model, and if it has yawed by 10 degrees, then this point would have moved by a considerable amount, while this point, let's say, did not move as much. So based on the new precise positioning, as long as you're getting a good accuracy on these, you can estimate what is the new heading of the vehicle based on these GNSS measurements. Typically, you would want to keep these measurement points as far away as possible. Okay, which means that our single board computer, which now has 3 GPS measurement boards, when we are connecting the antennas to it, we must ensure that one antenna is at the very forefront of the ship, the other antenna is at the very aft of the ship, so that you get the maximum distance between them in order to estimate the heading from these methodologies. Now, you'll also see there are some applications which use not just 2, but you can even go for a higher number so that you can get you can put them as a triangle, let's say in 3, and can get estimates for not just yaw, but even roll and pitch as well. You can try to figure out. Now, the single board computer which we have acquired in our guild does promise that we can get roll, pitch, and yaw as well, but we have to figure out what are the right conditions and when we can actually see that happen in the field. So that is something which is subject to disturbances, and we need to be aware about it. Okay, one of the advantages of having this GNSS heading is that it is not subjected to magnetic interference. One of the main challenges when we are putting this magnetic compass on board is that whenever we have any ferromagnetic materials near it, its performance will not be as good, right? Because let's say we are trying to understand based on the Earth's magnetic field, and if I have a strong iron, if my hull is made out of iron, then it's unlikely that my magnetic compass will try to show me the true north direction effectively. Similarly, let's say that if we have BLDC motors or motors which are running and high power they are drawing, those currents will generate magnetic fields which can interfere with your magnet as well. So therefore your compass may not be as accurate, right? Back in the day, people used to build ships with wood, and at that time magnetic compasses were good enough. But a GNSS heading does not suffer from these drawbacks, and you can get a much better precise estimate of your heading from this. But you have to kind of keep in mind that this may be sensitive to ionosphere disturbances, and there may be multiple path effects. Does everybody know what is an ionosphere? What are these ionosphere effects that I'm talking about? Have you heard the term ionosphere? What is an ionosphere?
It's part of the atmosphere, right? I think.
Atmosphere, yes.
Yeah, the part of the atmosphere with a lot of interference, which can cause a lot of interference in EM waves.
Yes, it can cause with electromagnetic waves, it can cause reflection of certain wavelengths, but at much shorter wavelengths, it probably does not cause as much interference. So, for example, let's say radio waves, right? They get reflected from the ionosphere. So, which means if I shoot a radio wave up into the atmosphere, I can actually ensure that it will reflect off or basically refract and come back and reach somewhere back on the ground. Which means I can now transmit information from here to there. Right? So that is why when you see radio broadcasting stations, they're mostly using these radio waves, and they're using the idea that the ionosphere can actually refract these waves and send something back to the Earth. Whereas if you look at the visible light spectrum, that is something that doesn't get affected by this because the wavelength is much shorter. They simply pierce through the ionosphere and make their way to the Earth's surface. So you can't twist or you can't kind of refract or curve a light in order to turn around and come back to the Earth. That is not possible, but you can do that with radio waves. So whenever we are using these GNSS satellites, we have to be sensitive to these ionosphere disturbances, and because of this refraction effect, there need not be a single path in which the GNSS satellite can transmit information which reaches us, but there may be multiple ways in which it can reach us. So that is why, as I said, when you have multiple paths coming in, you now have a flipping model. Your GNSS is believing yourself to be at one location at one time and switching to a different location at a different time and switching back at the next instant. So the switching phenomenon can happen. So these are the things which are quite challenging, and actually a lot of research is still ongoing with respect to positioning systems, especially much more accurate than a differential GPS. If you want a positioning much more accurate, it goes to reason that it's not always possible, and you have to have the conditions right. So please be aware about these, that these things can cause you to not have the so-called millimeter level accuracy which is promised on the sensors when you buy them. So you have to take them with a pinch of salt. Okay, magnetic compass. This is pretty straightforward. It is basically a small lightweight magnet that is balanced on a frictionless pivot. Usually this is called as a needle. Which points to the north direction, and it basically tells you what is the basic orientation, as long as there is no ferromagnetic interference nearby. Okay. But is the magnetic north equal to the true north? Not quite, right? The magnetic north of the Earth does not align perfectly well with the rotational axis of rotation of the Earth. Okay, so there is some difference. How do you account for that difference? Any thoughts?
Yeah, we find the angle between the two north. There is an angle actually, angle of declination of the
Angle of declination. What is that angle of declination?
It's the angle between the true north and the angle of that, the magnetic north.
No. That's something which actually changes on the Earth's surface.
Yeah.
So basically what is happening is when your magnetic needle is hanging, okay, it will not be straight. It will decline a little bit. And that declination is different at different points on the Earth. So there are charts actually which you can look up to figure out what is the declination at different locations on the Earth's surface. Using that declination along with the direction, you can try to compute what is the actual direction of the magnetic north compared to the actual north. And that information can be used based on the idea that you know the difference between the axis of magnetic axis and the Earth's rotational axis. So using that, you can figure out what is the correction which is needed, and that skew or bias between the two is called as the declination. But one has to keep in mind that whenever we are using a magnetic compass, it is extremely sensitive to magnetic variations, and then therefore we have to be aware about the fact that we should have no ferromagnetic interference nearby in order for this to work properly. That is where this new technology came about, which is called as the gyrocompass. So rather than believing in a magnetic north based on a needle, we now try to, today's compasses generally are what are called as gyrocompasses. So they do not, they're not susceptible based on magnetic field, but they are rather based on a slightly different principle. A gyroscope basically is a disc which is mounted on a base in such a way that the discs can spin freely on its x and y axis. Okay, so it's like a gimbal on which you have mounted the gyroscope, and then the gyroscope is spinning. Now, as long as the gyroscope is spinning, no matter how the base is oriented, however I try to move it, it will still maintain its same orientation. There's actually a very nice video by a MIT professor, I think Walter Moon, or what is his name? He's very nice video of it where he shows you this idea in action. Maybe I'll try to find that video and post it on Moodle so that you can take a look at it, where you can move the base all you want, but the gyroscope still keeps pointing in the original direction that you chose. It keeps pointing in that direction. So that can help us figure out that no matter what my craft's orientation is, if my gyroscope was pointing in a particular direction to begin with, it continues to point in that direction. So relative to that, I can now measure what is my angle. Okay, but this does not have anything to do with the magnetic rotation of the Earth or the magnetic field of the Earth. So therefore, you're able to avoid altogether disturbances in ferromagnetic. Ferromagnetic disturbances do not affect you anymore when you're looking at gyrocompasses. The problem with it, although, is that the original designs of these gyrocompasses, they were not susceptible to magnetic effects, but they were susceptible to the roll motion of the ship. Now, I don't know if you have seen this. I'll probably put a video for that as well. I know of a good video which talks about it, which is called the gyroscopic effect. Gyroscopic effect basically means that when you have a spinning wheel and you apply a force on it, it will turn in its perpendicular direction. So if I have a wheel which is spinning this way, okay, and I apply a load here, then this wheel is rotating like this, okay? It will not turn like this, but it will start turning this way. And that's a very cool phenomenon. In fact, you can try that out in our workshop. We have a gyroscopic effect demonstrator in our workshop. So you can come by, and there is a wheel which is attached to an axle. So hold the wheel horizontal, axle horizontal, turn the wheel by sufficient amount and let it go, and you'll see that the axis basically stabilizes like that and keeps rotating. Okay, I'll share a video which demonstrates this effect. So whenever you have roll motion, then this gyroscopic effect can start to bother your gyromagnetic compass, and it can start making some effects there, which is not advisable. So it's kind of not something which you want. So you have to have some mechanisms to avoid that. But over time, people have come up with ways to avoid that, and the designs today, gyrocompasses have become a standard issue on most vessels that you see at sea. Okay? They don't use a regular compass because we build ships with steel today. So therefore, mostly you will see these gyrocompasses being used. Okay, now, when we are making these measurements, so for example, let us say we are using these GNSS measurements, or we are using these so-called compass measurements, it is measuring the total effect of the entire environment. It's basically a sensor which is taking into account whatever is coming due to the external disturbances. So your craft may be experiencing motion due to waves, wind and current, and all those are taken into account, and whatever is the instantaneous position, that is what you're measuring from your sensors and getting it as an output. But that is not what you want to use in your feedback loop. And we talked about this when we were talking about control systems, that you don't want to wear out your actuators for the high frequency stuff. So you want to remove the high frequency stuff, and only for the low frequency motions you want to compensate. So for example, let's say a gust of wind is coming and pushing me off by 1 degree. I don't immediately want my compensatory thrusters to swing into action in order to correct for that. Or let us say that there's a wave coming at an oblique angle and my heading angle is oscillating at some particular wave frequency. I don't want my actuators to try to correct for it, or I don't want my rudder moving in order to correct for those disturbances. I want it to correct for the slowly varying and the mean varying, slowly varying loads, for which I want to maintain the same orientation. But a wave, we know, is a cyclical effect, which means it will just do this and come back in the very next cycle. Within that cycle, I do not want to do compensation. So it becomes important to separate whatever we are measuring into two components. We want to separate it into the low frequency components and the wave frequency components. And we are going to denote them by LF and WF respectively. So it is only the low frequency components that you want to really take into effect into your controller in order to do the control system's error manipulation. So there has to be a way to filter out these the signal that we measure into its low frequency and wave frequency components. And you'll see that these low frequency components have components due to the current, wind, and as well as due to the waves. And I think we have kind of spoken about this briefly when we were talking about modeling, that when you have waves of different frequencies, you'll see forces come up at some frequencies as well as difference frequencies. It is the difference frequencies which is coming at a low frequency regime which we need to be bothered about. It is the high frequency stuff which we do not need to bother about, and we want to filter them out. So this wave filtering is a particularly important aspect, and operations that require the control to be depending on the low frequency motions include the dynamic positioning systems, heading autopilots, thruster assisted mooring systems. Okay, so these applications typically require the low frequency motion to be passed back in the control system. Whereas you will also see that there are certain operations which require the wave frequency motion to be filtered out and used. So for example, if I want to do an active heave compensation, okay, which means that I want to transfer something from one vessel to another vessel, and as I do the transfer, I want the relative motion between the moving load and the moving ship to be zero, so that I'm not putting that down on the second vessel with a thud, but rather I'm putting it down smoothly and the contact forces are limited. In such a scenario, I actually want to know what the wave motions look like and what is the effective motion of that load, and then try to make sure that the winch on the wire is moved in such a way that the load stays perfectly balanced. So even though this ship might do things, that load should stay in its place. And you'll actually remember that Shrinik actually worked on this problem, and he tried to apply different controllers and compare different controllers to see how that can be made. So active heave compensation is one way to do that, where we require the wave frequency motion. Similarly, for passenger ships, you might be interested in a ride control in order to avoid motion sickness. Okay, and if that can be done using different ways. The control can be done using gyroscopic effect. So you may have a very large gyroscope or a flywheel which is rotating, and once the ship is coming in contact with the waves, because of the gyroscopic effect, the ship will not roll as much. So these are mechanisms where you're trying to figure out what is the wave frequency motion and compensate for it. So those applications require the wave frequency motions to be isolated, whereas the above ones require the low frequency motions to be isolated. So depending on applications, you do have to separate out whatever you're measuring into the low frequency components and the wave frequency components. And that separation basically is what we are interested in when we talk about this idea of wave filtering. Now, this wave filtering is done either by a state estimator or a filter, and we'll start discussing in the next class as to what are the different methods as to how to implement these filters in place. Particularly, we will look at something called low-pass filters. We'll also look at something called notch filters, which are like a band-pass filters, and how they can affect to signal or to filter out the unwanted frequencies from a signal and only give me frequencies which are relevant for my application. Okay, and you'll see that all of that has to do with more with Laplace transforms or differential equations in general. Okay, so in the next class, we'll start taking a look at the so-called low-pass filtering effects, and we'll also discuss about notch filtering, and then eventually we'll move down to what are called state observers, which are in the form of state estimators. We'll look at fixed gain state estimators, and then finally we'll cap it off with Kalman filters. Kalman filters is what is the traditionally used methodology today. Before 1960s, people were struggling a lot with this problem until Kalman came around with a beautiful solution where he can filter out and give you the best estimate of the state as an output. We won't go into the theory of Kalman filter again. We will try to keep it to the application orientation so that we can understand how to implement it for our applications. Okay, so that's all where we will stop today. Are there any questions before I stop? No questions? At least I hope that today has given you some thought process that sensors, how they work, is something to think about. It's not so straightforward all the time. We may think of something might be, oh, LiDAR, yes, time of flight, but maybe not. Sometimes you have to be a little careful and give it a thought as to whether what we are talking about is making sense or not. So I encourage you to now think as to what are the different sensors which we generally usually have on board on autonomous vessels, and how do they work actually, and how we can do the integration between multiple sensors is a very exciting area which is growing rapidly today. So we'll kind of try to see, we won't see any sensor, we'll see some sensor fusion in our course, but we'll not see too much of it, which is still a good area of research. But I think you have seen some of it in your VRX competitions. I think it has given a good taste of it. Okay, if there are no other questions, let me stop recording now.